Okay, we're going to continue on here, chapter 12. Almost near the end. All right, so in chapter 12, we're talking about some stuff. We're talking about alcohols mainly last time, I think. And we talked about in several chapters or several lectures, really, how we prepare an alcohol. So a reminder that we prepare an alcohol through really the hydration reaction of an alkene. So if we take an alkene which has a double bond and we add water, which is HOH, as we talked about, that is really how we prepare our alcohols. We make our double bond into a single bond, and that's going to make room for really our alcohol group there to come on. And in this case, it's not going to matter which one you put it on. You'll get the same alcohol here. And that is, again, how we prepare it. We go from an alkene, we add water, gets us an alcohol in this case. And as we talked about, that is ethanol. And we talked about naming alcohols, and much like double bonds, triple bonds, again, the OH group does take the priority. So you do want to find the longest carbon chain. It does need to include the OH group, and you do want to number the chain. And if whichever way will give the OH group the smaller numbers, what you're looking for in terms of the priority. In alcohols, we're usually looking at about 3 or more carbons that you do need to give the location of where the OH group is located. 2 or less there, like ethanol here, you don't need to, because it could only be on really 1 carbon in that sense. We talked about primary, secondary, and tertiary alcohols, and we talked about a primary alcohol, which is essentially an alcohol that is attached to one other carbon. So we talked about the oxidation reaction, which is sometimes abbreviated with that little kind of O in brackets there. And that is the definition of losing hydrogen. So remember that when you have an alcohol that goes through an oxidation, we always lose H2. And the hydrogens really always come from a specific spot. Always from the oxygen that has the hydrogen in it is where we take it. And we do take it from one of the carbons there, or the hydrogen from one of the carbons that are directly attached to the oxygen. That is going to get us our product here. And as we talked about a number of times, that when we sort of take away 2 hydrogens to allow room for a bond to come in this case, we do need to put the double bond sort of back in. So we remove that double bond to allow the hydrogens to come in, or when we remove 2 hydrogens, that usually allows us to make a bond. And we do need to make a double bond between the carbon and oxygen always. This creates an aldehyde, which is an organic group that has a functional group, as we'll talk about more today, hopefully, of that guy right there, the carbon, oxygen, double bond, and the hydrogen. And that, again, obviously is our alcohol. We also talked about secondary alcohols. And secondary alcohols are connected to 2 carbons, that OH group. And again, if we go through our oxidation reaction, we're going to grab an H from our oxygen, an H there from our carbon. And once again, nothing else changes as we talked about. Everything stays the same, except obviously here we do need to put our double bond in there between our carbon and oxygen. This will also give us H2 coming off. This gives us a ketone. So if you, again, oxidize a secondary alcohol, you will hit a ketone, which has the functional group basically of 3 carbons in a row and a double bonded oxygen in the middle of those carbons is the functional group of a ketone. So you got to have a 3 carbon run in a row, and in the middle there, that double bonded oxygen. We talked also about the idea of a tertiary alcohol, which again, as we talked about, will not go through oxidation as it is missing sort of a crucial hydrogen. That guy has no hydrogen, so that is not going to allow the oxidation to occur. So we'll get really no reaction here. If we try to oxidize a tertiary alcohol, we could only really oxidize a primary or secondary alcohol to make an aldehyde or ketone. We think also talked about at the end last time as well that really oxidation reduction, as we talked about with redox reactions in the regular chapters, they always sort of can happen together, which means if we were just heading in the opposite direction, those would be all the reduction reactions. So if you reduce down an aldehyde with hydrogen, you get back your primary alcohol. If you throw your hydrogen back on, or ketone, and we'll talk maybe a little bit more about that today as well, you will get your secondary alcohol. It goes back on the exact same way that you took it off. They end up those hydrogens at those locations. And again, you do have to get rid of the double bond in this case to make room for those hydrogens to come in. It's pretty much identical to like the addition reaction with hydrogen that we talked about with the double bond carbon, except here just have a double bonded carbon oxygen, but pretty much kind of works the same way overall. In the end result, it works the same way. I guess that's a better way of putting that. We also talked about dehydrations of alcohols, and dehydrations of alcohols basically means that we take out the water, and that is usually done through some type of heating process here. And we'll do something like that. So if you just apply heat, which is sometimes just a triangle in equations, it will dehydrate. And just like the water comes on, again, the water goes off the same way. So we take the OH, obviously, that is there. And again, here, the hydrogen does need to come off from the opposite carbon or a carbon next door to it. In this case, there's only one carbon next door that you could choose from. If there was one to the right and they have the same number of hydrogens, you could choose whichever hydrogen you want to the left or to the right, if it happens to be. Remember, if there are different numbers of hydrogen, you actually have to take it off the one with the least when you're removing the hydrogen. So opposite of when you put it on to the one with the most, the hydrogen, right? So it goes opposite that way. Clearly here, our water would come out. And once again, nothing's going to change. So all this is going to pretty much be the same. And the only difference is obviously we got rid of our water, which means we now need to throw our double bond there between the two carbons that we removed the water from. This is obviously the opposite of making an alcohol. This is going from an alcohol back to an alkene, right? So sort of the opposite reaction of the hydration reaction is the dehydration reaction. Any questions on any of those there? Okay, let's see. Let's see here. So a little bit more about some alcohols, methanol, which again, sometimes are referred to by their groups. So methanol is really a methyl group on there, sometimes referred to as methyl alcohol. It's rapidly absorbed and oxidized to formaldehyde. So it's kind of a forerunner to formaldehyde, which maybe if you're taking biology, you're familiar with. And you could also oxidize it to methanoic acid, which we'll talk about in just a second as well. And by the way, that does happen when we do prepare a primary alcohol and we oxidize it one more time. We do get a carboxylic acid, which is the last one there. And we'll talk about it in just a second, I think. Ethanol, again, is the one in alcohol there. And again, as we oxidize it here, we get our ethanol, which is a aldehyde. And if you oxidize it more, you get CO2 and water in that case. The next sort of group that we're going to kind of talk about are thiols, and thiols are actually sulfur-containing groups. So these guys contain sulfur. The functional group typically for a thiol is kind of like the alcohol, except that it is a sulfur attached to hydrogen rather than an oxygen attached to hydrogen. And if you've ever done anything with sulfur, it has a lot of smell associated with sulfur. That's what they put into gas, so you can smell it leaking. They put sulfur into gas so you can actually smell it. Without it, you can't really smell it. So that's, again, why they actually added to gas. And did it get up there? I don't know. Did the roll sheet get up that way, everybody? Yeah, we're good? Okay, perfect. Thank you so much. So you do need to know the functional group here of a thiol is, again, the SH group. And as you can see, they're kind of similar to our alcohol group. Naming thiols, I think we're going to pass on the naming of thiols, so you don't have to worry about naming thiols. But as you can see there, it's not difficult. You basically just put thiol at the end of the name. So if it has one carbon, that is methane, and then you put thiol at the end. So methane thiol, that is ethane thiol. But we're not going to worry too much about naming them. Longest carbon chain here is 4, which is butane. And that thiol group's on number 2, which is kind of like an alcohol to give the location. And that would be 2-butane diol, or butane thiol. So you don't have to worry about naming. You do have to worry about the functional group of it. And you do need to worry about the reaction that it could undergo. So let's talk about it here. We'll probably see it again in a second. But if you have a thiol, for example, and you had 2 thiols. So for example, let's just say we had this thiol here. And let's say we reacted it with another thiol. And they could go through an oxidation reaction. And the oxidation reaction that's going to happen here is the same oxidation reaction we've been talking about, which is we're going to take out hydrogen. And where we're going to take out hydrogen is 1 from each. That's why I kind of drew them back to back like that. Those are the 2 hydrogens that are going to come out. And then what is left is basically you're just going to squeeze them together. So you're going to take out the 2 hydrogens, push both sides together. And once again, this is one of those things where if you just copy what's there, you're going to be in good shape. So you just start there and go, okay, I have a CH3, I have a CH2, I have a sulfur. I obviously took that out. So I'm then going to my next sulfur and this guy here. This is basically what you will get. This is what is sometimes referred to as a disulfide bond, or sometimes referred to as a disulfide bridge. And there's some amino acids like cysteine that will make those in the body when 2 sulfurs come together. So you do need to know the functional group of a thiol. You do need to know this oxidation reaction. And as you might imagine, you could also go backwards on this one as well, which means that if I started with this guy, or this guy here, we'll go with that guy, and I added some hydrogen, and this is going to be a reduction reaction, what's going to happen is it's going to break apart exactly where we put it together. So it's always going to break apart between the 2 sulfurs. And you'll basically get 2 thiols as a result of this. You'll get the guy on the left there, which is CH3, CH2S, and we take one of these hydrogens that are here, and we put it on that guy. Then you get the second guy that's there where you broke it, and he also will need a hydrogen to make him a thiol. And that is all there is to that. So what we just did there when we add hydrogen back in to break a disulfide bond is basically break the bond always between the 2 sulfurs. Hydrogen goes to one, hydrogen goes to the other. Everything else stays the same, basically. Any question on that reaction there? I just wrote underneath because I ran out of room. So you can go side to side if you want. They're not attached. On the right, you're talking over here. Yeah, they're not attached. They're 2 different. Yeah, so there's a little plus there to indicate that they're 2 different things. Yeah. Other questions? All right, so why don't you try one here? Let's just do, let's do this on here. All right, let's say we had this guy here plus this one here. Okay, so let's take a look. So once again, this little symbol here, which is supposed to be an O, is oxidation is occurring. So remember, there's three definitions of oxidation, and in a lot of cases, it is the remover of hydrogen here. So if it does help you, sometimes it may just be easier to redraw both of these things and just kind of flip the other guy around, because you know that is sort of where um, we're going to get sort of the action happening here. And now if you kind of put them together in the right orientation, you could just box the two hydrogens that you need to remove. And that will give you obviously the hydrogen. And at that point, all you have to do is just kind of draw it just like you just did there without the hydrogens. So you just start with the CH3, CH2, CH2. This is going to make our disulfide bond there between our two sulfurs, coming over to the other side, CH2, CH3. So sometimes you just kind of set it together, box out the hydrogens, and then again, all you have to do is copy. And that's what you would want in this class, right, is to kind of make it easier for yourself, right? So don't forget, you got most of the drawings and all these reactions that we talked about kind of given to you in the reaction side. You just got to adjust it properly. So you got about 97% of it probably already there. Any questions on that there? This is going to be a reduction because we are adding hydrogen. So this is going to be a reduction reaction. So just like we take the hydrogen out, we break it right where we put it together. And that's basically just going to give us two parts. And all we have to do is put a hydrogen on each part in the proper place, which because these are thiols, it will go onto the sulfur always on this case. So we'll have our CH3 and our S. And again, this guy is going to get an H from here, for example. That will then leave us the other part, which is basically S, CH2, CH2. I got creative here, CH2, CH2. Regretting it right about now, CH3. And we have one more hydrogen that will complete this back to a thiol in this case. So these are not too bad reactions. Kind of take out the hydrogen, put them together. And then if you want to break it back apart, break them at the sulfurs and put the hydrogens back on. Any questions on that? Yeah. Yeah. It's either way. Yeah. It is technically, this would be mainly what I would probably be looking for, but you do get the hydrogen that comes out, and it's the hydrogen that you took out from inside. For the quiz, if you wrote that, I'd be extremely happy. If you put the hydrogen on there, that's good too. But really, I'd be looking for the main structure in that case. But you do actually get the hydrogen as well. Yeah. So you do get it. So if you want, you can put it in there. But the main thing I'll be looking at, like I said, is kind of the guy right there. Was that your question? Or yeah. So I'm going to say yes and no. If I may not understand exactly what you said, but if you said you wrote the answer like this, then that would be incorrect. So you should have kind of the like this to imply that the hydrogen is attached to the sulfur and not the hydrogen is sort of attached that way. So I would say no to that, if that's your question. If your other question was, do you have to then write this one in this direction? You don't. You could, if you wrote, CH3, CH2, 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 and SH, that's all good too, if you want that one. But yeah, so as long as you shouldn't probably put the CH3 and the H in the middle, then to the S. So you want to kind of do the S first and then the H on the outside of it. Yep. Other question? All right, so that's thiols. Skunky. All right, I like it. All right, so no naming, but those two reactions and the functional group being able to identify them as a thiol. The next organic group is going to be an ether. That is a functional group of carbon, oxygen, carbon. So you got to have that sort of run in it. A carbon, oxygen, carbon. By the way, this is not a double bonded carbon or anything like that. It's just a single bonded carbon or oxygen on both sides. So not a double bonded oxygen or anything like that. So carbon, single bonded oxygen, single bonded carbon on the other side of it. So that is an ether. And it has a bent structure like water, and that's because although a lot of times we don't draw the electrons are still there, and that gives it 4 electron pairs and 2 bonds, which gives it that bent or V-shaped type of geometry, that less than 109.5 degrees in that case. So how we're going to name these is we're going to go with the common name of these guys. It just seems easier. Why not? We'll do the common name of it. So the common name, which is not the IUPAC name here, we basically, as simple as it sounds, you just go to the oxygen and you look to the right and left and find the groups that are there, and you name them as groups. So that's a methyl group, right? That's a methyl group, and that's 2 methyl groups in the same thing. So that is a dimethyl, and you just put ether at the end. So that is a pretty easy way to do it. If you had something like this, for example, CH3, CH2O, CH3. If I go to the oxygen here, by the way, this is an ether because carbon, oxygen, carbon. So that's the functional group right there, COC. If we go to the oxygen, to the right is a methyl group, right? To the left is a ethyl group. And not surprisingly enough, we go alphabetical order here, right? So this is going to be ethyl, methyl, ether. So we'll go with common name. The IUPAC name is a little bit interesting, I guess. With the IUPAC name, you actually find the longest chain, which is would be in this case ethane, and that's like the base of your name. And for the other group, we drop the YL and put oxy, so that's like methoxy ethane is the IUPAC way of naming it, which is why we're going to go common names. These are much easier. So that is the way we will go. So we'll go common name, like I think they do in your book. But that's basically what you would do if you were doing an IUPAC name. In this case, they're both the same. So the base of the name would be methane, and it would be methoxymethane would be the IUPAC way of naming it. But we will go with basically group and ether at the end of it. Question on that there. So here, as we can see, if we come here, we'll focus in on the oxygen. That is a 3-member group, which is a propyl, 1-member carbon group, which is a methyl. Again, going alphabetical here, methyl, propyl, ether in this case. So if we had, say, something like what would that one be? And then if I could get the H in there without butchering it there, let's try that again. Let's do that. And then why don't you draw, let's do propyl. Actually, let's do they both start with P. Let's do pentyl, propyl, and ether. Okay, so let's take a look. Once again, if we're going to name an ether, first off, you want to make sure you can recognize that it is an ether. And just in case you can't, that is a carbon, oxygen, carbon right there. So that is what we're looking for to let us know that it is an ether. And that's that carbon, oxygen, carbon type deal. In that case, we are again going to roll with just the common names in this book, which I think is what it says here. So we will go to the oxygen. Again, we're just going to go left and right of the oxygen and just name those carbon guys as groups. So that is 1, 2, 3, 4 carbons. 4 carbons is based off of butane, so that's a butyl group, I believe. Over here is 2 carbons, which is based off of ethane. That's an ethyl group. And alphabetical here, we're going to go, we'll go butyl first, ethyl. And again, we're just going to lay up ether at the end of it. Any question on that one there? Now, if you're going to draw it, you would still work it the same way as we work anything else that we draw, which is going backwards. I will say we'll probably do a slightly different thing here, which is when you see it's ether, because it's a common sort of name. I personally, if I was going to draw this, would just start with the actual functional group of it, which is the carbon, oxygen, carbon part of it. So that's what I would start with, and I would just do, I don't know where I want to draw that. Go right about there, maybe carbon, oxygen, and carbon. Now, in this case, you could go, it doesn't really matter if you go to the left or you go to the right and put the next group or whatever you want to do. But each of the remaining groups are going to go either to the left or right, obviously, of that oxygen. Now, you do have to be careful here because of the way I did it. I already have a carbon, right? So I got to include that in my counting. I don't want to just go and put a propyl group onto the right and 3 more carbons, because then I'll have 4 carbons, right? Which is not what I need. So I am going to do a propyl to the right because that looks like I have not a lot of room there. I need 3 total carbons to the right. I already have 1 from the functional group, which means I just need 2 more, right? Now I could go to the left and put my pentyl group, which means I need a total of 5. I already obviously have 1 right there, so I just want to put 4 at that point. And that's going to be 2, 3, and 4, which gives me a grand total of 5 if I put 1 more there. 1, 2, 3, 4, 5. At this point, it's listed like anything else. Everything else is going to be hydrogen, right? And again, we're going to do that for our carbons. Our oxygen is going to be fine. We don't need to really do anything to the oxygen, so don't put any hydrogens on the oxygen. They have, although not usually drawn in our level or any level, but they have those non-bonding electrons on them, which is why they're okay. They don't need any hydrogens or anything like that. So we would need 3 hydrogens here at the end. We would need 2 for this guy. We would need 2 for this guy, 2 for that guy, 2, 2, 2, and 3 here at the end to give our carbons 4 bonds. Any questions on that one? Yeah. I did 3 on the right. That's going to give me my propyl group, which is a 3 carbon group. And then to the left here of the oxygen, that's 5 carbons, which would give me the other group that I needed. Now, if your question is, do you have to put the 3 on the right and the 5 on the left? You don't. You could do it the other way around as well. It's basically the same molecule, just turned if you drew it the other way. And you have that benefit of doing that, kind of like when we draw everything else, like if you want to call carbon 1 to the left or carbon 1 to the right, because you're drawing it, you have that option of whichever way you kind of want to do it. Yeah. Other questions? All right, so those are ethers here. Let's talk a little bit more about some ethers. Ethers are obviously used to put you to sleep, I think. Yeah, in a lot of cases. Gives patient a loss of memory, which is probably good if they're putting you to sleep, I suppose. Over the years, though, they have kind of swapped out a lot of the hydrogens on ethers with more fluorines, just some less volatile, less flammability, which is again probably good if you're sleeping, right? It's not so flammable, and you get a little better sort of result. But obviously, we use ethers as anesthetics to when you're doing surgery or something of that nature. All right, so why don't you draw these guys here? A little 3-pentanol, a little ethanol, a little diethyl ether, a little. Okay, so let's take a look. Remember, we're going to go backwards. So on the first one, we see OL. That should tell us it's an alcohol. Pentane is 5 carbons. So 1, 2, 3, 4, and 5. And 3-pentanol means that carbon number 3, that is where we find my OH group. And at this point, it's all going to be hydrogens here to get to 4. And that would be obviously the condensed formula. If you're going to do a little line structure, 1, 2, 3, 4, and 5, a little squiggly there. And number 3 there, we would do our OH there. So squiggly maybe. Question on that one there. Ethanol as well. OL tells us it's an alcohol. Ethane tells us it's 2 carbons. And because there's no numbers, it doesn't really matter which one you put the OH on. And we will have 2 hydrogens there and 3 there. And that would be our condensed formula. Guess if we're going to do a line structure, it looks something like that, perhaps. Diethyl ether. Again, here, the ether is where I'm going to really start when I draw this. So we know that is a carbon, oxygen, carbon. And again, diethyl means really I have 2 ethyl groups. I again want to be careful here because I already put a carbon on each side. So I need 2 carbons on each side. So I just need to add 1 more after I do the functional group. Again, if you add 2 more, you'll have too many. And now we're just going to hydrogen it up here. And again, oxygen does not need anything. And we have something like this. By the way, if we're going to do a little line structure on that, same idea. I would go oxygen. I would draw basically a line, which is my carbons. And then I would draw whatever else I need. Like so, yeah. Give me my other carbon in that case. So if you want to do the ether that way, it works the same way. Again, one more time in super slow motion. Oxygen, carbon, carbon, adding the rest of the carbons that I need off of those carbons. Yeah, it gets us to what we need there. Question on that. That gives us obviously 1 and 2, and 1 carbon, 2 carbons in that case. Yeah. Questions on drawing any of these here? Yeah. 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 You know what? I did draw it wrong. You're correct. There should be 1 more line down. So I felt like it didn't look right, and I'm gonna do the old teacher. I just want to see if you're paying attention. Clearly, I didn't screw up on that, but I did screw up on that. It should be something like this. Thank you. It actually should be like that. Looks a bit better, I would say in that case. Yeah. Otherwise, I just had 1 carbon, as you were about to say, and an oxygen attached to it, which would be actually methanol, or was what I had there. This would be ethanol. Thank you. That would be correct in that case. Yeah. Other questions? All right. Some of the properties of alcohols we've maybe touched upon, but just touch upon again. For example, isopropyl alcohol there is in things like rubbing alcohol. Ethanol is in there. And alcohols, as we talked about, can be classified, as we mentioned a number of times, primary, secondary, and tertiary. And based on that here, right, this guy here would be primary, secondary, tertiary. This one's going to be a secondary because of that carbon is attached again to 2 carbons, right? So it's going to be a secondary alcohol. And by the way, the name of that alcohol is it is 2-butanol. And that is because we have 4 carbons. OH group at carbon number 2 there, and we do need to give the location at about 3 or more carbons, right, with our alcohols. Here, this is going to be primary, secondary, tertiary. This is going to be primary again because this carbon is attached to 1 other carbon right there, and that's going to be, name is propanol. Do I need a number? I'm going to say yes. I'm going to need a 1 in this case because we could have our friend 2-propanol, right, if it's on the 2nd carbon. So you do need a number in this case. And again, starting about 3 carbons with our alcohols here. This last guy is going to be it is attached to 3 others. Name of this one is... That came out really quick. I'm going to see. I'm going to box that, which feels like the longest carbon chain. So that is 5 carbons. So that should be a pentanol. Yeah. And I got a methyl there. And that is my alcohol. Doesn't matter which way I go for my alcohol in terms of numbering. It doesn't. It's going to end up at 3. And really doesn't matter which way I go for my other one either, because it's going to end up at 3 as well. So that's going to be the 3-methyl, 3-pentanol. Yeah. Any questions on that name there? Yeah. Good practice, I suppose. Yes. Let's talk a little about the solubility of alcohols. Again, because alcohols have that OH group, it does make them fairly soluble in water, which also has that OH group. And again, the oxygen being more negative, hydrogen being more positive, it is going to be able to participate in, as we probably have talked about previously, hydrogen bonding. And because it has that and it's able to participate, and the alcohol is not very large, it's going to work okay with water. Again, in order for something to be really soluble in water, it has to basically replace water and water interactions, which are hydrogen bonding together, with similar interactions. And usually, if it's not too large of a molecule, it's going to work really well because of that. Solubility does pretty much decrease with the nonpolar part of an alcohol. So obviously that's the nonpolar part, which is the carbons and the hydrogens. That is our polar part. So if you get something like this here, what ends up happening is, frankly, the nonpolar part is just frankly too big. And it's too big, it gets in the way, sometimes referred to as steric hindrance. It's a hindrance and doesn't allow water to sort of effectively get in there to interact with the OH, because you got this little small part that's polar and you got this really big part that is non-polar. In addition, as I mentioned before, water is a relatively small molecule. So when you're trying to get something to be soluble with water, it needs to be of similar type sizes. So I often use this example of, like, if you have a garage, you could, get a car in there, as all works well. You could try to park a semi truck in there and you get part of it in there, but the rest just not going to fit just right. And that's sort of what happens when you get these really large molecules. Although it may be able to interact a little bit, it's not going to be able to interact very well and not going to be really soluble because it's just really too big for it to interact. So usually right around, I would say, 5 or more carbons, you start to get the solubility of, say, alcohols to really drop to like nothing. With that being said, if you have like a alcohol that has a bunch of OHs in it, so multiple OH groups, that actually increases the solubility. So for example, if you had something like this, where you had, maybe something that has 2 OH groups on it, the solubility of that guy would definitely be much more soluble than somebody with 1 OH, because anywhere there's an OH group, it gives it an opportunity to interact well with water, and it's basically able to make it more soluble. That's why something like sugar, for example, which we might saw when we were just talking about solubility in general, it's a relatively large molecule, but it's littered with OH groups all over it, and it makes it really, really soluble, because everywhere there's an OH group, it gives it a place to interact with water, and it can do hydrogen bonding with water. So you can see upwards of about 4-ish, you're good in terms of solubility for alcohols, but above 5 and more, pretty much going to become insoluble. And again, we're talking about the carbon part of the molecule. When that gets too large, the solubility really starts to drop. By the way, I think we also talked about it, but just a reminder that because alcohols can actually obviously hydrogen bond with itself as well, again, through our hydrogen bonding here, the positive to the negative side, typically alcohols have really large or high boiling points and melting points. So alcohols, again, are pretty much the champion in terms of melting points and boiling points for organic molecules, especially in comparison to things like alkanes, alkenes, alkynes, even really ethers as well, because they have the ability to hydrogen bond. That's almost the right answer. And every question to ask you, why does this have a high boiling point or melting point, is because it has the ability to hydrogen bond, and that's usually the right answer in most cases. So because of its ability to hydrogen bond with itself, it is a relatively strong attraction, which means what that means is if you wanted to get it into the gas phase, you have to break that bond, and that's going to take a lot more energy to do so. The result of that is going to be at a higher temperature to get that much energy to break it, and it'll have a much higher boiling point and melting point because of the ability to hydrogen bond. Phenols, which again, as we talked about, are benzene rings that have the OH group on it, are slightly soluble in water. And again, because of they have that sort of benzene ring, doesn't help out a lot with solubility. But you will get more of like an acid base reaction that will sort of happen in this case, where this is going to kind of donate the H plus over to the water, kind of like our Bronsted-Lowry definition that we talked about with acid and bases. That's going to happen here, and you'll get basically some H3O plus that will sort of happen in this particular case. All right, indicate whether each of the following should be soluble in water or not, and explain. Would the first one be soluble in water? It would not, although it is an alcohol, although it does have that polar bond, it has a lot of non-polarness right over here. And because of that long non-polar chain, it's going to make it probably insoluble there in water. How about the second one? Second one's good to go. It's smaller here, less than 4 carbons. And again, it's got that OH group at the end of it, which again is going to allow it to interact really well with water molecules through hydrogen bonding. Again, a reminder, hydrogen bonding is intermolecular forces, which are basically opposites attract, right? Positive one side, attracted negative side of the other. And that's basically what's happening here. The hydrogen in the water is positive, the oxygen is more negative. So there's an attraction that occurs and allows them to interact well with each other. All right, any questions on alcohols and thiols and ethers? All right, we're going to then hit a couple more organic groups, subject of lab this week, I think. We're going to talk about aldehydes, which have this functional group, the carbon-oxygen double bond and a hydrogen, and our friend the ketone that we talked about, which has a functional group of 3 carbons in a row, and it's got to have that double bonded oxygen there in the middle. So the simplest ketone, which is known as acetone or propanone, is a dimethyl ketone. It is colorless, it is odorless, or has a mild odor unless somebody opens it perhaps in a car when they want to take their nail polish off, right? It's happened, right? You know, nail polish remover as well, by the way. Even though some are non-acetone based, they still kind of smell like it. So a lot of solvents have those type of things. You definitely can smell them. The IUPAC name for these guys and common names for aldehydes and ketones are based off of really this important group. So both the aldehyde and ketone contains what is referred to as a carbonyl group. And a carbonyl group is a polar group, and it is the carbon-oxygen double bond that we see in these guys. And the oxygen part is more negative, and the carbon part in that case is more positive. So it is sort of a polar sort of bond happening between the carbon and the oxygen in this particular case. We obviously have talked about how we make an aldehyde or a ketone. And we can make an aldehyde through the oxidation of our primary alcohol, right? So we have our primary alcohol that we talked about. I guess I should put a carbon there, would be good. There we go. And through our carbon here that gets oxidized, we're going to remove our hydrogens, and we will end up with our double bonded oxygen and our hydrogen and our aldehyde. So again, a primary alcohol oxidized to an aldehyde will give you that. By the way, we can also take the aldehyde, as we will see, and oxidize it one more time, and we actually will get another organic group, which is known as a carboxylic acid. And that is this functional group right there, the carbon-oxygen double bond with the OH. So we could actually oxidize that aldehyde to one more step, and we'll talk a little bit more about it as we go through. We could get our ketone by our secondary alcohol oxidation, as we talked about earlier. Again, oxidizing our secondary alcohol through the loss of those two guys, making our double bond happening here. And that will get our ketone. By the way, if you oxidize a ketone, you do not get a carboxylic acid, by the way. So I will not go any further in that sense. That is the simplest one, as they were talking about on the previous page, in terms of a ketone that you could have, because you need 3 carbons in a row. So the simplest one you could have is something to do with propane that has 3 carbons in a row. So you can't have like a 2-carbon ketone or a 1-carbon ketone. Now, this group is important in terms of some things like solubility and bonding, boiling points, as we will talk about. Now, when we talk about the aldehyde and the ketone, there is a difference in terms of sort of the locations of where you find the functional groups. So for example, our aldehyde here, its functional group must always be at the end. Why can that functional group never be in the middle, attached to more carbons? What is at the end of this functional group? Yeah, and hydrogen can only have 1 bond, right? Which means it can never be in the middle anywhere. So if you have this functional group, because of that hydrogen, it's got to be on one end of the molecule, or it's got to be at the other end of the molecule. It can never be in the middle, this functional group. So if you by some chance see a double bonded carbon oxygen there, and it's in the middle, and you think it's an aldehyde, it cannot be if there's more carbons on either side. Because again, this group has to be at the end. With that being said, you will never find for a ketone the carbon-oxygen double bond at the end either, because the ketone needs the 3-carbon run, which means the closest you could get to the end for that carbonyl guy is second in. So you could always, that's the closest you could get to the end. So you'll never find the carbon-oxygen double bond at the end in a ketone, because in order for it to be a ketone, it's got to have 3 carbons in a row with the carbon-oxygen in the middle. And that's different than an aldehyde, where you will always find basically the carbon-oxygen double bond at the end of the molecule. So because of that hydrogen that is there in the aldehyde. Any questions on that there? Now, our aldehyde and ketone, in terms of drawing them in line structure, I'm going to do better than I did before. Hopefully, we'll see. So if we do something like this, this is going to be a ketone in line structure, as we have a carbon, 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 right? So that is sort of what it will look like. If we have, I need to put an H there, right? Because now I have a carbon, hydrogen, double bonded H, right? Or double bonded oxygen there in that particular case. So again, if I don't put the hydrogen at the end, that's going to be another carbon, right? So you do have to put the hydrogen there. And as you can see, this is at the end. This is in the middle, basically, right? So of this particular one, or second in, at least from the end. So let's talk about naming them. For an aldehyde, we basically just drop the last part of the name and we put Al at the end of it. Now, there are some common names, like formaldehyde is 1 carbon. So for example, if I had this, that is 1 carbon, right? And 1 carbon is based off of methane, and this would then be methanol, right? If I had 2 carbons, say like this, that is 2 carbons, which is based off of ethane. That is ethanol, Al at the end of it, aldehyde. Although we do not need to give the location of where the carbon-oxygen double bond is located, and that's because it always has to be at the end. That also means, though, that the carbon-oxygen double bond should be carbon number 1. Yeah. So whichever side it's at, that should always be carbon number 1. And that's important for other groups that may be attached, right? So if he has to number it, you want to start numbering that way. And if there are other groups there, then like normal, you would give the number where those groups are located in alphabetical order. So, if we had something like maybe this. The base of this name would be 3 carbons, right? Because that contains our functional group here. And that would be our propanol. Because this has to be carbon number 1, because that's where the carbon-oxygen double bond is located. That means that my chlorine is at carbon number 2. So this would be 2-chloral propanol. And again, you don't need to give the number for the aldehyde group here. But it is going to be carbon number 1, no matter where it lays up. Any questions on that there? All right. I would say out of these kind of common names, I would say, like I mentioned before, methanol, formaldehyde is also methanol. They're the same thing. So those are the same guys. For our aldehydes here, let's take a look at some here. Let's just draw some. Let's do okay, let's take a look. We'll start the first one. Probably straight across here. 1, 2, 3, 4, 5, and 6, right? So we have our functional group there at the end. Again, that is our aldehyde group, as that is a carbon right there. So we know this is an aldehyde. We got 6 of them, which means hexanal. We also know that this carbon where the double bond is should be carbon number 1, which means that carbon number 2, carbon number 3, that is a methyl group. Carbon number 4 and carbon number 5 is a bromol group, right? So now we have our location. Alphabetical here, we're going to go with the Br first. So we'll do a 5-bromol, 3, maybe squeeze it, methyl, hexanal in this case, yeah? Any question on that name?
Do we have to, like, the drawing on top, do we have to draw the line for the H where the double bond O is?
I would say you should. If you don't, technically speaking, it's implied that it should be there. But just to be safe, I would draw the line. So you're asking, I think, can you technically? Are you asking? Can you just technically kind of just do that type of thing?
Yes,
without the line. Technically, it would be implied that there's a hydrogen there, but probably best still to draw the line for that one as well. Yeah. Other questions? All right, so let's take a look at the next one. Longest carbon chain is. It is 1, 2, 3, 4, 5. Yeah. So again, you want to make sure you check all the options and not just the straightest one. So that would be 5. I would agree with that. That is a pentanol, I believe. Again, there is our functional group, which means that is actually carbon number 1, which means my methyl group is actually a carbon number 3 in this case. And that's going to give us a 3-methyl pentanol in that case. Yeah. Any questions on that? So this one is not 2 or 3-ethyl butanol or whatever you might call it. Yeah. To pick back up here, any questions so far? Anything we've been talking about here? All right. So as we've been talking about, again, we are going to do the IUPAC way of naming the aldehydes, which is what we just were doing Again, a couple of things that we talked about. We'll always find in this group at the end because of that hydrogen. And although we do not need to give the location of the carbon-oxygen double bond or that carbonyl-carbon, which, by the way, that is what this carbon is sometimes referred to. The carbon in that carbon-oxygen double bond is referred to as the carbonyl-carbon. That carbonyl-carbon is always going to be carbon number one in purpose of naming any other groups that may be attached there. Again, that methanol and formaldehyde are probably the ones that you do need to know of for sure. Okay, so let's take a look. So obviously we're looking for the longest carbon chain. And as we saw in the previous one, make sure you do check all your options. But in this case, it is this right here. It obviously does need to include the functional group as part of the longest carbon chain. That's going to give us, it looks like a 5-pack there, and that is our aldehyde group right here. So that's going to be, again, a pentanal. Remember, it's Al, not Ol, because that is an alcohol in this case. We will end up here with this being carbon number 1, which it always should be the carbon-oxygen double bond, or again, sometimes referred to as the carbonyl-carbon. That is going to be right next door at carbon number 2 then, which is our methyl group. So that's going to be a 2-methyl pentanal in this case. Any questions on that there? So let's talk about our friends, the ketone. And the ketone gets ONE at the end of the name. So same as everything else, we're going to look for the longest carbon chain that obviously contains the carbon-oxygen double bond. We're going to drop the E and put ONE at the end of it. So our simplest one that we could have, obviously, as we saw earlier, is this guy here. And that is going to be 3 carbons, which is based off of propane. We're going to drop the E and it will become propanone. ONE. Surprisingly enough, just like a ketone is ONE at the end. So that is, again, how we name these guys. Now, unlike the aldehyde, because the carbon-oxygen double bond or that carbonyl-carbon can actually be in multiple locations, you do sometimes need to give the number, kind of like what we do with the OH group and double bond, triple bond. You do have to give the number of where the carbon-oxygen double bond is. I will say, if we look here, that is 4 carbons, which is butanone. And because it needs 3 carbons in a row, it could only really end up on the 2nd carbon in each case. If you did it to the left, and I guess what I mean is if you drew it like this, or you drew it like that, no matter which way you number it, the carbon-oxygen double bond is number 2, which means in the case of ketones, that's about 5 or more carbons. You need to start giving the number of where the carbon-oxygen double bond is. Brings us to our friend pentanone here. And if we look at it here, that is 1, 2, 3, 4, 5. And the location here, 1, 2, and 3. So that is 3 pentanone. Now, you may be wondering, why do I need 3 pentanone? It is because of maybe this. What would the name of this one be? This one would be 2 pentanone, right? So we still got 5 carbons, but now smallest number for this guy here gets the priority. It would be 2 pentanone. So right around 5 carbons with ketones, just like our OH groups with alcohols and double bonds, triple bonds, you do have to give the location of where the carbon-oxygen double bond's located. Just like everything else, we want to give it the smallest number. So whichever way gives it the smallest number. And just like everything else, if there happens to be other groups attached, whichever way you number to give that guy the smallest number, everybody else is numbered accordingly. So again, once you lock in your numbering, you do not change it. That is a ketone there on a ring. That sounds like fun. All right, so that's a ketone on a ring there. So let us dissect this name. That is based off of cyclohexane. It has a ketone, which is right there, by the way, carbon, carbon, carbon with a double bond in the middle. And that now becomes cyclohexanone, ONE. In this case, do I need to give the location of the double bonded oxygen? I do not, because it's a ring structure. But because it's a ring structure, wherever that guy is located should be carbon number 1. And then that would give us our shortest distance to our group, which is our methyl in this case. And that would give us our 3-methyl cyclohexanone. So if it happens to be a ketone in one of those cycloalkanes, you don't have to give the location of the carbon-oxygen double bond, but it will still be carbon number 1 for any other groups that are attached. Once again, that is not benzene, as there is no double bonds in that ring, right? So again, that is cyclohexane based off of. Any questions on that there? All right, so why don't you give the name of this ketone? Okay, so let's take a look along this carbon chain. If we go straight across, 1, 2, 3, 4, 5. You could also go 1, 2, 3, 4, and then go down as well to give you 5. Once again, it doesn't really matter which way you choose. It should really give you the same answer regardless. I personally am a fan of just taking the straight one there if you have one. That way you can kind of put a box or highlight it. Obviously here we then have a group that's a methyl group hanging off of it. So that is 5. It is a ketone group, as we can see right there is our ketone group, basically. And that is going to be a pentanone. Do I need to give the location of the carbon-oxygen double bond in this case? I do, because that's 5 or more. So that would be carbon number 2, which locks my numbering into going in that direction, which means that's going to be carbon 3. And that puts my methyl group at carbon number 4 in this case. So that's going to be a 2-pentanone. And then that's going to be a 4-methyl 2-pentanone. Yeah. Any question on that name there? Yeah. So let's just do a few more here. Just rando make up some stuff here. Let's see. I don't know. I don't know how I want to randomly do it. Let's just do like that. I don't know. We'll go that way. I don't really know what I'm drawing. I feel like I'm just drawing carbons. Could be. Let's hope for the best. We'll see. Top one here, I believe longest carbon chain right about there, which is 6. It contains our ketone group, which is right about there, right? So that is our ketone group happening. So that's going to be something. I feel like I just lost it. There it is. That is 6, which is going to be hex. No, NE. Do I need to give location of carbon oxygen double bond? I do. In this case, we want to go left to right to give it a smaller number. That's going to give this group here, which is an ethyl group at carbon number 3. And our hexanone will be carbon number 2, where our carbonyl group is. So that's going to be a 3-ethyl 2-hexanone in this case. Any questions on that one there? I'm sorry? Oh, there is a CL. Thank you very much. That would be good. I'll not forget about him. Then that would be a 5-chloral. Good thing alphabetically comes first, I suppose. So 5-chloral 3-ethyl 2-hexanone. Yeah. Any questions on that one there? This is actually a aldehyde, right? So that's an aldehyde, which means carbon 1, 2, 3, and 4 carbons. So that's going to be a butanal, Al. No need to give the location in this case because it should be at the end, but it is carbon number 1. I will try not to forget the chlorine in this case. That means that is at carbon number 2, and that's going to be a 2-chloral butanal. Yeah. Questions on that one there? That is a cyclopentane ring that has a ketone group off of it, which is carbon, 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 and our double bond, right? So right about there is our functional group happening there. So that's going to be a cyclopentanone. As I scribbled all over it here. Let me just erase some of that maybe. There it goes. We can maybe see. Now, again, we don't need to give the location in this ring structure for this guy, but that is going to be carbon 1, which means coming this way is going to give me the smaller number for my methyl, and that would be a 3-methyl cyclopentanone. Any questions on that one there? Longest carbon chain on the next one is? It is 6. Didn't get you, huh? This time we'll go this way, right? That's good. So that's going to give us 6, which contains our ketone group here, which again is right about there. So that again is going to be a hexanone. There, I drew the same thing, just look different. There's no chlorine on this one, so that's good at least. That's also still going to be a 2-hexanone because that's going to be a carbon 1, carbon 2, carbon 3 is where my ethyl group is. See, maybe I was just naming the other one first. There we go. 3-ethyl 2-hexanone should be the name of this one here. Any questions on any of those names there? All right, let's draw some. See how we do on this. Let's do, I don't know. Let's do 3-propyl 2-heptanone. Let's do 2,2-dimethyl cyclopropanone. Let's do 4-methyl 5-propyl. Once again, we're going to start backwards here. ONE tells us it's a ketone, which means it should have a 3-carbon run here. Heptane tells us it's 7 carbons. 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Again, since you're drawing it, you can go in any direction you like. I'm going to go left to right, which means this is going to be carbon 1. 2-heptanone means I should have my double bond right about there. That will take care of that part of the name. And because that's going to be carbon number 2, a carbon number 3, which would be right next door, I should have a 3-carbon group, which is my propyl group. Once again, everything else is going to be hydrogens. So we'll do 2 there, 2 there, only 1 there, none there, 3 there. And then we'll put our hydrogens onto here as well. Questions on that one there? That obviously is our condensed formula. We have cyclopropanone. Once again, ONE tells us it's a ketone. Cyclopropanone is based off of cyclopropane, which is 3 carbons in a beautiful triangle arrangement. And because it is a ketone, perhaps we should put a double bond in there. And that would give us our carbon, carbon, carbon type of deal happening there with our double bond. Since that is going to be carbon number 1, I could go left for carbon number 2, or in this case, I could go right for carbon number 2. It doesn't really matter. And I'm going to lay me up a couple of methyl groups there, obviously without the C's usually. So, something like this. Or obviously you could have done it to the one to the left, which would have been the same. Yeah. Any questions on that one there? Lastly, that is octanal. Al tells us it's an aldehyde, which has a carbon oxygen H. So in this case, I need 8. Those you regret after you write it. 4, 5, 6, 7, 8. Did I fit it there? 1, 2, 3, 4, 5, 6, 7, 8. We know we should have that group at the end. And again, you're drawing it so you can put it on the left end, you can put it on the right end, just to mix it up. I'm going to go on the right end here and put it. That means for me, because I put it on that side, that is going to be my carbon number 1. If you put it on the other side, then that would be your carbon number 1 on the other side. And because that's carbon number 1, I'm going to go 5 carbons over. 1, 2, 3, 4, 5. I'm going to put a propyl group here, which again is a 3-carbon group. And I'm going to go to carbon number 4, which is actually 1 before, and lay me up a methyl. I might just go below because it looks easier. Doesn't really matter. And now we're going to fill in some hydrogens here. This guy just needs 1. This one needs 1, 2, 2, 3, 2, 2, and 3 in that case. Any questions on any of those there? Questions on how to draw ketones, draw aldehydes, name them? No. All right, then let's talk about aldehydes and ketones in water. Aldehydes and ketones can hydrogen bond with water, although it cannot hydrogen bond in a sense like you might think. The hydrogen bonding is actually happening at the carbonyl group. So that carbonyl carbon, as we talked about, is more negative, more positive on the bottom. So when we get water, it is still able to hydrogen bond through the positive side to the negative side. And this is still hydrogen bonding to the carbonyl group. So that does help with soluble. So aldehydes and ketones are going to be soluble in water. Again, same sort of issue as long as they're not giant. So, I again say 4 or less, you're going to be good in terms of the solubility. As you build out more carbons, like most things in organic, even something soluble is going to pretty much drop off and not be soluble, just because the non-polar part is bigger than the polar part, basically, and it makes it not able to really be soluble. So that's what we see here, upwards of almost like 4 for sure. 5, you're getting to the point where slightly soluble, which is kind of considered insoluble. And past that, you're going to get into some things being insoluble because it's really large. Although they can hydrogen bond with water, ketones and aldehydes cannot hydrogen bond with themselves, and they don't have the ability to do that. That means in terms of boiling points and melting points, your alcohol is still going to beat them because the alcohol can hydrogen bond with itself. So alcohols are still going to beat these guys in terms of boiling points and melting points because of the lack of the ability to hydrogen bond. But these guys are going to do pretty well because they could still do some dipole-dipole interaction, which is still relatively strong. So they definitely will have higher melting points and boiling points than just like your alkanes and your alkenes and your carbons and hydrogens, all non-polar guys. So these guys will still have a good boiling point, melting point, but our alcohols will still beat them because of its ability to hydrogen bond. So if you're kind of keeping track of boiling points, melting points at this point, you got like your alkanes, all your non-polar guys, your alkenes, and then you got your aldehydes, your ketones, and again, your alcohols still sort of at the top there, boiling points, melting points, and alkenes, alkynes, and alkanes are going to be more on the lower end of boiling point because they're going to still use those dispersion forces, which are relatively weak forces. Here's our acetone and our formaldehyde, as we talked about. Acetone, which is propanone, I would say also that is a name that's still used a lot, acetone, obviously. So you should know that if somebody says acetone, that it is propanone, which is a ketone. So those two, as we talked about, kind of common names for those two things. Formaldehyde is methanol, and acetone is propanone. Those are two things that you should know, that they're talking about basically the same thing. A lot of aldehydes and ketones have aromatics. And here is our ketone, again, carbon, carbon, carbon with the double bond. That's our aldehyde here. Things like vanilla, cinnamon, there, and almonds as well are our aldehydes. So some of the good stuff in perfume and fragrances are found from there. So let's classify each of these as aldehydes or ketones. First one is it is a ketone, right? As we got carbon, 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 double bond there in the middle. B is a aldehyde. Again, functional group right there. C is also a aldehyde, functional group there. And D is a ketone. Again, carbon, carbon, carbon with the double bond in the middle there. So that is a ketone. That is what I would say is oftentimes missed by people in the ring sort of ketone. Sometimes people don't not sure really what it is, because you can't see the carbons, I guess, because they don't really put them out there. But again, you do have that 3 carbon. You can actually have an aldehyde, and typically an aldehyde will sort of be drawn like off of it like that. Yeah. Yeah, it was sort of specified on that. For example, if this was benzene, that would be known as benzoaldehyde, like the benzene ring. So benzoaldehyde, and typically you'll see it's kind of like drawn off of it, the aldehyde, because again, it needs that hydrogen to be kind of by itself and nothing on the other end of it, as opposed to here where it kind of incorporate the rest of it. Yeah. Other questions?
That one was not. Oh, that one over there was not benzene.
Yeah.
How would you name it? Was like a hexane group.
It would be cyclohexanal. Al at the end. That's how we name aldehydes. It's connected through here, the carbon to the carbon in that case. It would actually, that would be still part of the longest carbon chain. It would all be together, and it would be incorporated more like a cyclohexanal Al, as that whole thing is, even though you're thinking of it more like a group kind of hanging off of there. Yeah, but it wouldn't. It would be more thought of in this case as more the functional group as being part of the whole thing, kind of like in a sense, kind of like when you have all the long carbons and you have the OH. I know it's an oxygen versus a carbon there, but we sort of think of it as, you know, all being together as one thing. That would be more so how you would go about probably naming that guy. Other questions? All right, let's actually, I'm going to skip ahead a little bit just to talk about something, and then we'll cover some of these other things, which we already covered, actually, most of this here. We'll come back to it. But I did want to talk about those reactions that make, for example, an aldehyde and a ketone. So as we saw earlier, once again, we're going to start with our primary alcohol. And we're going to oxidize it. And this definition of oxidation, again, is that hydrogen that's going to be taken off, and that is going to make our aldehyde here. As I mentioned earlier, you can continue to oxidize the aldehyde one more time. But the definition of this oxidation is actually the gaining of oxygen is actually going to happen here. Now, I'm going to clearly way simplify it and just tell you there's a lot more to it. But what's going to happen if you take an aldehyde and oxidize it, you're just going to basically toss an oxygen right there where the H is and keep the H as well. And everything will stay the same, except that you're just going to insert an O there. And that is, as I mentioned before, going to give you another organic functional group, which is known as a carboxylic acid. And that is the functional group what I just sort of highlighted. It is sometimes written in formulas like that, like COOH, and that COOH is what is boxed. So if you see it in a formula and you want to draw it, that's basically what it looks like. This is a carbon-oxygen double bond. By the way, in terms of our name, this is our friend ethanol. This is our aldehyde with his ethanol. This is our carboxylic acid, which is ethanoic acid. You kind of drop the E and put oic acid at the end of the alkane name. So that's what's known as ethanoic acid. By the way, the carboxylic acid group, much like the aldehyde group, always has to be at the end because of the hydrogen. Yeah. As we will talk about when we talk about carboxylic acids, that is your champion in terms of boiling points and melting points because it has the OH group and it has the carbon-oxygen double bond. It actually is the one thing that could be in an alcohol in terms of boiling points and melting points because of the presence of these two groups. Now, with that being said, we talked about our secondary alcohol being oxidized into a ketone, which again, we're going to remove our hydrogens and make our ketone, which again will give us our 2-propanol and our propanone. In our case here, if we go to oxidize it, we're not going to get a reaction that's going to occur. So we'll just say that. So there is some tests that you can do, for example, which you're going to do in lab this week, where you could test for the presence of a carboxylic acid. And if the carboxylic acid is there, what that means is what you started with was a aldehyde. Now, if you test it and the test is negative, in the case of your lab, what that means is you probably started with the ketone here, yeah, versus the aldehyde. So one of the tests that you're going to do is not this one. So we'll talk about this one. We'll talk about the other one next time as well. But this is what's referred to as the Benedicts test. And the Benedicts test is a reagent that takes copper 2, which is kind of a bluish color, and it basically will go through an oxidation reduction reaction. And what's happening is the copper 2 in this case, which is a blue color, will be reduced and it will then make a copper 1 ion, which is, dare I say, a very ugly color of orangish, reddish, kind of pukey looking color, depending on what you got going on in your lab, but kind of an orangey type color is what it's going to be. So if you use the Benedicts reagent in a aldehyde, it will actually oxidize the aldehyde to a carboxylic acid. So it will take that aldehyde to a carboxylic acid. So if you did the Benedicts test on this one here, actually this part of it here, you would be a positive test for it. It would go from a bluish color to a orangey type color. And that would be a positive that a carboxylic acid has been formed and you started with an aldehyde. Now, if you threw the Benedicts reagent in with this guy, it would not turn that orangey color because this guy will not get oxidized. The reason it will not get oxidized is, frankly, it's missing the hydrogen that you need for the most part. And it will not go through an oxidation, kind of like a tertiary alcohol. And you would have a more blue sort of solution probably, and it'll be a negative test. So what that looks like, just to kind of show you here to finish up on, is this here. If you take the Benedicts reagent, which is basically it's blue because of the copper 2 ion that's present, and if the oxidation reaction occurs, because oxidation reduction occur, the copper 2 goes to copper 1. I would say more in practice is more of an orangey type color than a red, but you might get a red depending on your reagents. And that would be positive for, in your case, a positive for an aldehyde negative test would tell you started with a ketone. So I think you're going to do that test this week. So I just want to talk about it here, and we'll talk more about it next time. Any questions on that there? Yeah.